So our method today is going to be properties of gases, determination of the molar mass of a volatile liquid. And this is by way of the Dumas method. The reason I've got this timer going is this camera of mine cuts out after about 50 minutes. So I set it for 45-minute alarm, and when that thing alarms, I'll stop the video, change the batteries, we'll get started again. All right, so this is a very, very simple procedure, and once you know what's required, you'll think it's simple too. I'll talk about the theory in just a minute, but first of all, the hard copy document doesn't have a table in it for your data, right? So I've created a table up here on the board, right here, and these are all the items that I think we're going to need to do the calculations. All right, so what do the calculations look like? Well, that's what the pre-lab questions are for. Actually, this sample calculation here, the example, actually, let's do it this way. We're going to need two equations. The first one is the ideal gas equation. And the second one is the equation for molar mass, which I call molecular weight, which is mass of the substance and divided by the number of moles. Okay? So the document here takes this one and solves it for moles. Moles over here, molecular weight over here. And then substitutes in there for that one. So that gives us the ideal gas equation for mass divided by molecular weight times the gas constant times temperature. And then if you solve this for molecular weight comes over here, excuse me, M W, and then this goes over there, so that puts mass times R times T divided by P times V. And that way you can solve the molecular weight with one equation. So what we need is the mass of the gas. We need to know how much the gas weighs, and that will go here. Right here, we need these two values to get the difference. This is without the gas in it, and this is with the gas in the container. And this is the mass of the gas. Okay? R, of course, R equals 0.08206 liter atmospheres per mole K. Temperature is the temperature of the gas in the flask. So what's the temperature of the gas in the flask? Well, if you've already read the method, you know that the temperature of the boiling water bath is the same as the temperature of the gas inside the flask. All right? So that's why we measure the temperature of the water bath, because it's the same as the temperature of the gas. The pressure is what is the atmospheric pressure, the barometric pressure. And my barometer reads in inches of mercury. Right, so inches of mercury is going to have to be converted to atmospheres. Milliliters is the volume in the flask, and the method tells you to use the density of water, and you weigh the flask before and after and get the amount of water in mass and convert it to volume. I think it's just as easy and just as accurate under these circumstances to directly measure the milliliters of the volume in the flask. And we're going to do that. And then you convert the milliliters to liters. Okay, so we need pressure, we got temperature, volume, or mass, and we can calculate the molar mass of the gas with those values. Okay. Let's see. I'm not going to do the pre-lab questions. You can do those yourself. So here we have, once we determine the molar mass of the gas, you're not going to know what liquid it had produced the gas. It has to be a volatile liquid, one that has a boiling point less than the boiling point of water. Right? So when we heat it in a water bath, then we're able to volatilize the gas, the liquid, completely into a gas. That's essential. So once you determine the molar mass, you can pick out which liquid it is from this. All I'm going to give you is a number on the bottle. And then you take that number and you say, this is my number, this is what I think the gas or the compound is. Okay. So I've got some special notes here. You have to get the correct atmospheric pressure. You can't assume it to be 1 atmosphere, especially when you're above sea level, right, like we are. And you have to make sure the outside of the flask is dry after you take it out of the water bath. Otherwise, that extra weight is going to bias your results. Let's see. The volume of the Erlenmeyer flask is nominally 125 milliliters, but that's up to a mark on the flask. We're going to fill it up all the way to the top because that space is the space that's occupied by the gas. And then you have to be sure that the liquid is completely vaporized. You only want gas inside the flask before you take it out of the water bath. All right, so let's do this. Okay, here's our water bath. Here, it's got boiling chips in it, so we make small bubbles instead of one great big bubble. Here's our flask, and I think what I'm going to do is glove up for 2 reasons. One is some of those liquids, volatile liquids, are irritating, right? In the small amounts we're going to use, they won't be particularly toxic, but they are irritating. Plus, I don't want to add any fingerprints onto our flask before we weigh it. And thirdly, this gives me a layer of protection when I'm working around boiling water. Okay, so we need to be sure that this flask is clean on the outside. All right. It's got to be dry and clean. Now, what does the procedure say? I'm going to try to stick to the procedure, except for the measurement of volume. Right? That's going to be a direct measurement. We got the water bath prepared. We got the ring stand with a clamp. Now, why do we need a clamp? Well, when we try to submerge this in the water bath, it doesn't want to go, right? It's going to try to float, and we need to submerge it as far as it'll go. So we clamp it in here and hold it down. All right? So what's our sample? Well, we could just pick one at random. right? Let's see. Let's try this one. That's number 4, right? So let me make a note of that. This is sample number 4. Okay? And it's got some tape on it. That's because it's a volatile liquid, and we want to be sure that we don't lose it all over time. So there's our sample, number 4. Okay? Determine the mass of the clean, dry, 125 milliliter flask, along with the small aluminum foil and the piece of copper wire that we use to tie it. Right? So what I need to do is, let's see, I don't know if my scissors are strong enough to cut this thing. That's a thick wire. But let's see, how much of that wire do we need? It needs to go around like this. That'll be good. Okay, so let me see if I can chop this wire with my scissors. Get it started and then bend it. Maybe it'll break for me. There we go. There's my copper wire. Now, why do we need 2 pieces of aluminum? It says a small piece, 2.5 by 2.5 inches, and a 4 by 4 inch large piece. Well, this is the one that we're going to include in the weight. Right? All of that together. That's the weight without the gas. Then we're going to weigh it after the experiment, after the boiling, and that'll be the weight with the gas. But we use this larger piece because once we get that small piece covered, we're going to cover it completely with the big one. Why? Because in a boiling water bath, you got water vapor coming up there. And if we completely protect this lid with that one, then we can keep condensation to a minimum around this inner piece. And when we take that one off, which we do not weigh, then all we have to do is dab the drops to be sure that we have removed all the moisture. We're going to use rubber bands to hold the big one on there. All right, so we need a mass for this arrangement. And it needs to be as accurate as we can get it, which is going to be hard to do with these balances, but those are the breaks. We're probably only going to get 2 decimal places. I hope that's enough. We shall see. All right. My goodness. Why is it drifting? Oh. Because it sits too high. Let's see if this makes a difference. Nope, it still touches. We're going to have to use a different flask. Let's see if I can find a shorter one. Because we need to weigh it with the lid closed. Otherwise, we've got air currents that are messing with our readings. Let's see. Here's a shorter one. It's kind of dirty. Do we have any cleaner ones? Let's see if we got cleaner, shorter ones. Yeah. Might be a little on the heavy side, but I don't have any choice. Let's try this one. Let's try wiping it off a little bit. There we go. And it's dry. Has to be dry. All right, let's check our 0 point. Okay? Now, we need the foil, the copper wire, and the flask. And let's see, does it touch the top? No, we're good. All right, 71.87 grams. 71.87 grams is the empty flask with just the flask and the cap. 71.87, did I say? I gotta stop talking and remember. Yeah, 71.87. Okay, the next time we weigh it, it's going to have the cap on it, and it's going to have the gas, which by that time we'll have condensed back into a liquid. But that's okay, we're just looking at mass at that point. All right, so let's do this, there. Now, next thing we knew is to measure about 3 milliliters of the liquid. Now this doesn't have to be exact, right? We just need enough so that when it volatilizes, it will fill the space with gas, and any excess will come out through the little pinhole that we're going to prick in it. So let's give it 3 milliliters. I'm going to give it a little extra. This is a pretty volatile liquid. And that'll give us a little extra time to deal with it. Okay. Here we go. And I'm going to wrap this up. To be sure that it doesn't evaporate on us in storage. Okay. That was number 4. Yes. Okay. Now we're going to put this in the flask. Okay. And we're going to cap it with our aluminum foil. And we're going to be sure it's sealed off right here. This is pretty stiff wire. I bet I can just wrap it like that. Normally if it's thin wire, no, that's not going to work. We're going to have to twist it. Okay, so let's pull it out and twist it. There we go. And then put the sharp ends back down like that. Now, that's still the container, but now it has some liquid in it. Well, that doesn't do us any good because that liquid is not gas yet, or it's not gassy enough, and it's still got liquid, so that would bias our results. So now we need to cover all this. Well, I didn't plan on that breaking. Cover this and that there. Hopefully, we'll pay it very close attention after this and be sure we've got all the moisture removed. All right. So there we have our flask. Now, how are we going to be sure that we have only gas in there? Well, we need a little pinhole here that's small enough to let the gas out as it evaporates, but not to let any air back in. We want that space completely filled with gas. Right? And we're right down to the edge of the top of the flask, so that's why we need to measure the volume of this after we're finished. And it has to be volume all the way to the top, not to the 125 milliliter mark, but all the way to the top. Right? So, no, that's not, I don't use that. I got a little pin here in my Swiss Army knife. And we're just going to poke a pinhole through both foils. Like that. That's plenty big. All right. So now, we've punched the hole in it, and we're ready to clamp it and submerge it in the water bath. So let's go back like that. Let's clamp it down like this. Let's see, let me back up so you can see a little better, I hope. We don't want it popping up. Now, before we submerge it, let's check the temperature. It appears to be boiling, so let's see what the temperature is. In degrees centigrade. Okay, still climbing. Now, is it going to be 100 degrees? This is distilled water. Is it going to be 100 degrees? No, because we're not at sea level. Boiling point depends on atmospheric pressure. Right? So it's going to be less than 100 degrees. How much less? Well, I could calculate it, but I'd rather measure it. Okay, we're still going up. It's set on 97 so far. Let's give it a couple more swirls, see if it stabilizes. Yeah, 97. Okay, now what's going to happen when we put this flask in there? It's going to absorb heat from the water and probably stop it from boiling. Right? So, right when we take it out, we remeasure the temperature. That's the temperature that corresponds to the gas inside, not the temperature I just measured. That was just my curiosity. Okay, now let's submerge this thing in water like this. That's as deep as we can get it. It's not ideal, but it'll have to do. Now, how long do we wait? It says, let's see. It's just telling us to look, see if the liquid's gone. I think we need to go about 5 minutes or more. If we don't wait long enough, and sometimes you can see a density difference coming out that pinhole, but I don't see it. It's difficult. Now, there's another way to do it. You put a colored compound in there. It's called dithiazide, which is very expensive. That's why we're not using it. And the colored compound, once all the liquid is gone, the colored compound is also gone, and it goes from a color to colorless. And then you know that you've got only vapor in there. But this is only a community college, so we can't afford that stuff. A little tiny bottle is like $100. So we're just going to give it some time. Let's see. It's already been a couple of minutes. Let's give it another 5. I was watching my timer. And be sure. Okay, the water's still boiling. That's good, because we want to measure the temperature as well. Okay, we'll come back and get that. While we're waiting, let's get the barometric pressure. So here's my electronic barometer, and it reads out in inches of mercury, 29.41 inches of mercury. 29.41. Inches of mercury. See that? Okay. I'm going to pause for just a second and check my camera. Still recording. That's good. The battery's about half gone, so I'm right on schedule. Put this thing back on and continue. All right, let's not waste any more time. So, how long has it been? It's been about 3.5 minutes. And I can't see anything else in there, but let's give it a full 5 minutes and be sure we only have gas in that container. So here are the different volatile liquids that I have to choose from, and we picked number 4. So once we find the well, the first thing you notice is all the boiling points of these liquids less than 100 degrees, actually less than 90 degrees, which is good. Then we're going to determine the molar mass using this procedure and try to match the molar mass with the liquid, the particular compound. Okay, about another minute. All right. Let's start measuring the temperature, so when the minute's up, we'll be able to pull it out with a temperature. Temperature of the gas is the temperature of the boiling water bath. It's on its way, 97, okay. How are we doing? Oh, it's warmer, 98. Okay. Check it again. 99. All right. If it makes it to 100, I'll be surprised. Very surprised. And suspect this thermometer of reading wrong. Right, it stopped at 99. Okay, so that's our temperature, 99 degrees. And now we're going to pull this out of here. And let it cool down. Turn the water bath off. And we'll just dab some water. A lot of it, we hope, will evaporate. But this thing has to be room temperature before we can measure the weight. Because if we don't, if we put a hot piece of glassware on the balance, it will never settle down. It's very sensitive to temperature, and it'll create drafts, and it'll transfer heat to the balance and the load cell, and it's just a mess. So it has to be room temperature. We'll let that go for now. What else can we do? Temperature, 99 degrees. So let's put that up here. All right, 99 degrees C. We still have to do the volume of the flask. We have to get the weight after. And once we get the volume, we'll have all we need to do the calculation. It's still warm to the touch. We have to wait. And of course, what we're supposed to see is as this thing cools, we can take it out of the clamp actually. As it cools, the vapor of the liquid inside should recondense, and the gas inside will condense into a liquid. It's still too warm. All right, so we have to wait. We can close some things up. This is one experiment that doesn't produce a lot of cleanup. While we're waiting for that to cool, I can put some things back. So I'm going to put the boiling chips away, and I'm going to put the copper wire back where it belongs. And copper wire. Here we go. My goodness. Staying warm a long time. Alright, we don't need this anymore. And here it goes. In fact, I think I can put the buckets back in the drawer. This one belongs in this set. This is number 7. And number 6. Getting there. Still a little too warm. So let's put this away. There you go. You know what I'm going to do while we're waiting? We're going to pause. I'm going to change the battery. And I'm going to pick it up again when it's time to weigh the flask and check its volume. So I'll be back in just a second. I'm back, and the flask is cool. So now, we have to weigh it again. Do we weigh it like that? No. We take off the outer layer, because it was not weighed the first time. All right, so we have to take off the rubber band and remove the outer layer. And inspect it for moisture. So I think it's pretty clean. There we go. Okay, so now let's weigh it again. Set on 0. And good, there's clearance. 72.18. 72.18. All right. So we gained a little bit, not a lot. That's okay, gases don't weigh much. The real test will be when we do the calculation. and see if it looks reasonable. Okay, we'll subtract that later. Right now we need to get the volume of the flask. So to do that, we have to take this contraption apart. Like this. Like that. And it needs to be cleaned. That's a pretty volatile liquid. I think if I just sit it there, it'll evaporate on its own. And in the meantime, I need to get a graduated cylinder that is large enough to measure that volume. But I don't want too big, because if it's too big, this looks like a good candidate. 250 milliliters. So right in the middle somewhere is where we're going to end up with our volume. So let's see. This is, let me see what the divisions are. 2, 4, 6, 8, 100. So each one of these divisions is 2 milliliters. All right. Yeah, I still smell something. I'm not going to tell you what I smell because that'd give it away. Because these volatile compounds have a distinct odor. And several of them you can identify by smell. That's good. Now, let's bulk fill it and then top it off with our wash bottle. All right. Getting there, getting there, getting there. And let's finish it off with the wash bottle. All right. Be nice if we didn't have any bubbles in there. Okay. I don't think we have enough bubbles in there to add any more uncertainty than we're going to get from that measuring device. So let's fill it up, and we want to fill it up right to the brim, because that's where the inner aluminum foil was situated. All right, a little more. There we go. Right to the brim. Now, let's transfer that as efficiently as possible. There we go. Now, let's see if we can take a reading here. Say 130. This line is 140. 2, 4, 6, 7. 147 milliliters. 147 milliliters. Okay. Now, while we're here, let's get the difference. I could probably do it in my head, but it's late in the day, so I'm not going to take any chances. 72.18 and subtract the other one from it. I get 3.1. 0.31. Cheap chalk. Okay. Now, we've got all our data. So, what are we going to do? Well, we got to do some conversions, don't we? All right, I still got time before my next required meeting. All right. So, barometric pressure, 2941. 29.41 inches of mercury. How do we convert that to atmospheres? We need a conversion factor. Inches of mercury. How many inches of mercury is 1 atmosphere? Well, I happen to know that value. 29.92. Okay? 29.92. So 29.41, enter, 29.92, divide, 0.983, 0.983 atmospheres. Okay? That one's converted. How about milliliters? How many liters is that? You'll be able to do that one in your head. 3 places. 1, 2, 3. 0.147 liters. Notice I preceded that decimal by a 0. Never write a number with a decimal dangling out in front. If you don't have any numbers out here to put, 0 goes there. Without that 0, we call that an orphaned decimal. And orphaned decimals are forbidden. How about temperature? 99. How do we make Kelvin out of that? Plus 273, right? Plus 273. So 273 and 99 is 372. Okay? Grams is fine because molar mass is grams per mole. All right. This is the way you would solve the problem in one calculation. What you're actually doing is using the gas equation to find out how many moles there are in that gas. So we could plug in the pressure, the volume, the temperature, find out how many moles there are. Then you would take the moles, put it over here, and the mass, which you've determined, and calculate the molecular weight. So that's a 2-step process. This is a 1-step process. Right? So the 1 step would be mass. What's the mass of the gas? 0.31. What's next? R. 0.08206 liter atmospheres per mole K. What's next? Temperature, 372 K. Then in the denominator, right here, pressure is what? How many atmospheres? 0.983. And volume. What's the volume? 0.147 liters. Now, this is in the denominator, numerator. That cancels. This cancels atmospheres. This cancels liters. Then we have grams up here, and moles is in the denominator. The denominator of the numerator is the denominator. So that gives mass divided by moles. So we know our units are right because we canceled this one, this one, this one, this one, and that one, that one. So what do we get? Do the calculation. 0.31, 0.08206 times that, 372 times that, then divide by 0.983. 3 and divide by 0.147. 65.5. 65.5 grams per mole. Now I'm doing all this work for you, but when you write your report, you better have all this stuff in it to prove that you knew what you were doing. 65.5. Okay, we need our list. We need our list. Maybe I shouldn't do this. Let you figure it out. Actually, there's nothing in here that matches it. What's the closest one? That's the question. Okay. So what we have is experimental error. But getting the right value is not as important as doing the right method in this case. So what I want to see in your report is the proper sections to the report, followed by, you got the procedure. Let's go through them one at a time. You got your introduction. Why are you doing this thing? You got your safety blurb. What are the safety concerns? You've watched this whole procedure. What are your concerns for safety? Then the procedure. What did I actually do? Not what does the method say, what did I do? In third person, passive past tense. And you have an example of that. I gave you an example report. You know what passive past tense is because it's right there on the page. Okay, that's the procedure in numbered steps. What actually happened? Then you follow that with data. Right? We collected data. There it is. Got to have your data. Then you have calculations. What calculations were performed? Derive the formulas. If you're going to use that single formula, you better derive it. Show me that you know what you're doing. Then once the calculations are done and you show me that you've calculated the value, then you give me conclusions, summary and conclusions. And there may be some questions in here, right? Post-lab questions, pre-lab questions, those need to be in there too, and clearly identified so I don't have to hunt for them. Okay, that's it for the Dumas method, and I don't think we were very accurate in our calculations, in our procedure, but those are the breaks. If you identify any places where you saw errors being made, maybe I made errors and didn't notice them, make note of those errors in your report. Okay, that's it, and good luck.